Okay, let's dive right into this. I want you to picture something for a second. Imagine a Formula One pit crew. When that car comes screeching into the pit lane, every single microsecond matters, right? There is absolutely zero room for hesitation. No room for generic, unpracticed actions. Every single movement, every turn of a wrench, every tire swap is calculated, it's precise, and it is executed under immense, heart-pounding pressure to get that car back out on the track. Well, today, we're taking that exact same high-performance, pit crew precision, and we are applying it to one of the most notoriously tricky areas of the Cambridge computer science syllabus. Welcome to our explainer on special purpose registers. Specifically, we are mastering the status register strategy. Now, when we're looking at actual Cambridge past papers, and I'm talking across the board here, from foundational codes like 0417, 0478, 0983, 0984, and 2210, all the way up to the beast that is the AS and A-level 9618 paper 2, we constantly see two very specific types of students. Let's call them Alex and Sam. Now, Alex treats the exam paper like a massive data dump. He looks at a question, panics slightly, and just overloads his answer with raw computer science facts. He writes down everything he knows about registers, but he provides absolutely zero analysis, no context. And what happens? The examiner's red pen just slashes right through it. Then you have Sam. Sam treats the exam like a chaotic 100-meter sprint instead of a calculated Formula One race. Sam rushes. Sam completely misses the specific command word requirements, words like evaluate, or justify, or trace. He just sees the word register and starts writing, completely losing out on massive points. If you put their papers side by side, it's painful. Their flawed answers just bleed marks. But listen, today we are going to fix that. We are going to transform those red pen marks into green check marks using the ultimate exam timing and execution strategy. Let's get the clock started.
So you might be asking yourself, why are we focusing so heavily on this specific topic today? Well, here is the magic number, 15%. The status register and its associated operations account for approximately 15% of the total marks in paper 2. Let that sink in for a second. 15%. In the highly competitive world of Cambridge examinations, 15% is not just a handful of marks that you can afford to brush off. It is literally the massive gaping canyon between a B and an A star. It is the difference between missing your top university offer and securing it with flying colors. The stakes here are incredibly high. Going back to our Formula One analogy, the status register acts as the critical telemetry of the CPU. Think about it. It is constantly updating with every single calculation to tell the entire system if there's been a carry, an overflow, a negative result, or a zero. It's the diagnostic heartbeat of the processor. If you, sitting in that exam hall, don't understand how to read this telemetry, your entire exam strategy crashes into the wall. Every single mark counts, and we simply cannot afford to leave 15% on the table just because of poor, unpracticed pit stop mechanics. We need to be clinical.
All right, here's our roadmap for this session. First up, mastering core principles. Second, we'll dive into the method mark strategy. Third, we're going to run through the deconstruct, solve, evaluate loop. And finally, we'll wrap up with the absolute gold, top examiner warnings. Let's hit the gas.
Section 1. Mastering core principles. Because look, before we can start shaving precious seconds off our exam time, we absolutely must master the architecture of precise definitions and causal relationships.
Okay, so the theoretical framework of the status register isn't just about rote memorizing what a flag is from a textbook. It is about deeply understanding the strict causal chain of events. When the arithmetic logic unit, the ALU, performs the calculation, the status register instantly updates its flags. Boom! It is pure cause and effect. If you understand this architecture deeply, you can simply apply the core principle to whatever weird, wonderful, or complex context the Cambridge examiners decide to throw at you. By definition, the status register is a collection of individual bits, or flags, where each single bit represents a specific condition resulting from the most recent ALU operation. It is absolutely vital for multi-step calculations and evaluating binary conditions. Again, think of it as the dashboard warning lights on your race car. Now, to really encode these complex register concepts into your long-term memory so you don't blank under pressure, I always recommend the visual story method. Try this right now. Picture the processor executing a massive binary addition. The numbers are just too big. Suddenly, a tiny flag pops up in your mind's eye, a flashing red warning light, the overflow flag. It's screaming, hey, the result doesn't fit in the given two's complement representation. By actively visualizing these flags, the carry, overflow, negative, zero flags as physical warning lights responding to an engine's stress, you encode the multi-step calculation process dynamically. You aren't just passively reading ones and zeros anymore. You are watching a machine react in real time. That is how top-tier students think.
Notice the massive difference here between isolated puzzle pieces and a fully connected conceptual picture. This perfectly highlights the gap between our hypothetical student Alex and the top-tier candidates who get those A stars. Alex has isolated knowledge. He knows the textbook definition of an overflow flag. But the moment Cambridge gives him a scenario, say about a temperature sensor in a nuclear reactor failing, he totally freezes. He doesn't know how to connect the flag to the sensor. Top-performing students don't just memorize, they reference cross-topic connections. They seamlessly transfer their knowledge to entirely unfamiliar contexts. And how exactly do they do this under the ticking clock of an exam? By using a specific, practiced framework to structure their answers. We call it the PEEL framework: point, evidence, explanation, and link. It works like this. You make your point about the binary condition. You provide evidence extracted directly from the data given in the question. You give your explanation of the underlying computing theory. And crucially, this is the magic step. You link it back to the exact scenario Cambridge provided. I'm going to challenge you to spot this PEEL structure in action as we move through the interactive workshop later in this explainer. But before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
All right, moving into phase 2, the method mark strategy. Now, what's really interesting about this next concept is that it fundamentally changes how you approach every single complex mathematical and algorithmic question on your paper.
You need to realize that you are being judged on your procedural sequence. Just like a pit crew is evaluated on the exact, flawless sequence of their actions, tires off, new tires on, secure the bolts, drop the car, Cambridge examiners are actively looking to award you marks for your process, not just your final outcome. If you document your methodology clearly, you can secure up to 80% of the marks for a specific question, even if your final binary digit is off by one silly little mistake. Here is the strict 4-step procedural framework for tackling any status register exam question from past papers. Step 1. Deconstruct the question. What is the command word? Is it describe? Is it evaluate? Or is it trace? Step 2. Extract the data. Pull the relevant binary strings out of the dense text. Step 3. Execute with notation. Write down your working out clearly, showing exactly how the ALU shifts bits or adds them together. Step 4. Present with terminology. Use correct professional terms like most significant bit or carry out. If you look closely at the exam papers from students who jump from a C grade to an A, you actually see the red pen marks transforming into green check marks simply because they started showing their working out using this exact 4-step blueprint. They stopped hiding their thought process in their heads and started putting their methodology on full display for the examiner to reward.
Let's put this into a practical workshop setting right now. I want you to imagine a complex Cambridge data table sitting on the screen in front of you, filled with raw binary representation showing the state before and after an arithmetic shift. We're going to run challenge 1, the data scan. If you have a watch or a timer, I want you to mentally put 60 seconds on the clock. Go. Your challenge in an exam is to extract the core trend from those binary representations, perform the calculations in your head or on scratch paper, and draw evidence-based conclusions before the clock runs out. When you are staring at an 8-bit register, you need to systematically scan from the least significant bit on the right all the way to the most significant bit on the left. You have to ask yourself, did a 1 fall off the end during a shift? Did it go into the carry flag? What does that mean for the next step of the algorithm? You need to deliberately slow down your reading speed here. I know the clock is ticking, but the command words and the raw binary require meticulous data interpretation skills. Do not rush the extraction phase, or your subsequent calculation will be completely useless. You're just building a house on a bad foundation. Take those 60 seconds, scan the data, and lock in your variables.
Now we shift gears into the practical application of algorithmic thinking with our third section, Deconstruct, Solve, Evaluate. But real quick, stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, let's get into the problem-solving loop.
What you're looking at is a 5-step problem-solving engine. This isn't just for exams. This is used by top software engineers, and it is strictly required by Cambridge examiners for rigorous testing and efficient code implementation. Step 1. Identify the given information. Step 2. Break it down into logical steps. Step 3. Solve systematically. Step 4. Check for reasonableness. Now, let's pause on Step 4. This is huge. If your status register indicates a negative number, but your algorithm was supposedly calculating the surface area of a physical object, well, your result is not reasonable. You can't have negative surface area. You must catch that. And Step 5, justify your recommendations. Think back to our friend Sam from the beginning, the one who rushes. Sam skipped Step 4 and 5 completely. If we ran challenge 2 right now, a find the flaw challenge, and I showed you a sample paragraph where a student correctly calculated the binary addition but completely failed to state that an overflow error occurred, that omitted sentence is exactly where they lose the final, crucial marks. They did the math, but they didn't justify what it meant. You absolutely must complete the loop.
And this brilliantly illustrates our next point. Evaluating algorithm quality isn't just about getting the right answer. It relies heavily on identifying these 4 key elements: time complexity, space complexity, edge cases, and their effect on overall performance. When you manipulate the status register, you are operating at the absolute lowest level of space complexity. It's just a few bits. It's incredibly efficient. But you absolutely must consider the edge cases. An edge case in this context is the extreme boundary of your operating parameters. For example, what happens when you add the maximum possible positive integer in a 2's complement system to the number 1? It doesn't just get bigger, it flips to the maximum negative number. That edge case causes an overflow. If your algorithmic evaluation in your essay response doesn't explicitly mention how the system handles that specific status register flag during an edge case, your evaluation is considered incomplete by the examiner, and just like that, your race is over. You've lost the points.
This brings us to our final and perhaps most critical section of this explainer, top examiner warnings. It is time to get very serious, because I'm going to give you the inside scoop directly from the principal examiner reports. These reports are the confidential post-race debriefs, where the people grading your actual papers detail exactly why thousands of students failed to achieve their potential. They see the exact same errors year after year. Here are the top 3 exact pitfalls where students just bleed easy marks. Mistake number 1, forgetting to check overflow and edge cases, which we literally just discussed. Students just naively assume the data will always fit perfectly. It won't. Mistake number 2, missing boundary conditions. This is when students don't test what happens exactly at the absolute limit of a register's capacity. And mistake number 3, listen to me, this is the biggest one of all, providing answers without context. This is Alex's fatal flaw from our earlier example. Theoretical knowledge without application is entirely useless in paper 2. If we were doing challenge 3 right now, a speed writing challenge, I'd put 30 seconds on the clock and tell you to write one perfect Peel paragraph explaining a status register change. If you only give me the textbook theory and you don't link it to the specific robotic arm or heating system or conveyor belt mentioned in the prompt, you fail the challenge. Theory is great, but application is what gets you the A-star.
I want to read this direct quote to you with absolute authority because it is that important. Straight from the grading floor. Examiner alert. The classic mistake is providing generic answers, not specific to the question context. Always link every point to the given scenario. So the crucial point is this. Cambridge is not testing if you are a walking dictionary of computer science terms. They don't care if you can recite the textbook. They are testing if you are a capable, analytical computer scientist who can solve real-world problems. The status register is just a tool in your toolbox. If a question asks about a factory conveyor belt system, your explanation of the zero flag must explicitly state how that zero flag stops that specific conveyor belt. The generic answer gets 0 marks. The contextualized, PL-structured answer gets full marks. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to at acetheexams_IGCSE and click that bell. Don't let another exam pass you by.
So, as we wrap up this pit stop, I leave you with this final provocative thought to carry into your exam practice. Every single time you finish writing a response, I want you to physically look at your paper and ask yourself out loud, is my answer linked to the scenario? If your paragraph could belong to literally any past paper exam from the last 10 years because it's so generic, you need to cross it out and rewrite it. Keep analyzing, keep applying the Peel framework, and keep linking every single fact back to the context. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here. Keep racing, and I'll see you in the next session.